All right, this video lesson is on velocity and speed. So what we're going to do is differentiate between the word speed and the word velocity. And the way that we're going to do this is by identifying whether or not these terms are scalar or vector quantities. So very similar to when we were talking about distance versus displacement. So we're going to head back to that same example that we actually used to differentiate between distance and displacement to talk about the difference between speed and velocity. So we've got the boy who's walking his dog who takes this curvy red path and the girl who is walking in the straight line. Imagine both of these people took the same amount of time to finish their paths. So they started at the same time and they stopped at the same time. My question that I want you to think about for the next couple of minutes, or not couple of minutes, I guess next couple of moments, is who would have to travel faster for them to start at the same time and then stop at the same time? Okay, so hopefully you're kind of having some sort of idea of who might have to travel faster. If you thought that the person who traveled the red path, had to travel faster, you'd be right. They did have a faster speed. And in everyday terms, that's how we describe motion, is how far someone gets in a certain amount of time. So our permanent, or our scientific definition for speed, is the rate at which an object travels a distance. The more distance traveled in a certain amount of time, the faster the speed. This is a quantity that's a scalar quantity, because it doesn't have anything to do with direction as much as it does with the amount of length traveled in a certain amount of time. So what about this girl who follows the straight line? How would a physicist interpret her motion? Well, she would have the faster velocity, because while she didn't travel as far, her displacement was in fact greater than the boy walking the dog. So her velocity must be greater than the boy walking the dog. Let me explain. Velocity is the rate at which an object changes its position. So the more that a position changes in a certain amount of time, the higher the velocity. Since displacement is a vector quantity, it depends on direction, velocity is also a vector quantity. So the way that we're going to differentiate between calculating speed and calculating distance is very simple. The average speed of an object is going to be its distance traveled divided by its time. This is what makes it a rate. Whereas for velocity, my average velocity is going to be my total displacement divided by the total time. Dividing my displacement by time is what makes velocity a rate. Now you might have noticed that I called both of these averages and that I even highlighted that word. The reason both of these are averages is because it doesn't tell us anything about the speed or velocity during the travel. An average speed or an average velocity assumes that the speed and velocity did not change at all during the point of travel. In other words, an average assumes that it's constant, whereas we know in real life that's not necessarily the case. Objects tend to speed up and slow down during their travel. So an average is just really a description from beginning to end and doesn't tell us anything about what happened in between the beginning and end of travel. That being said, let's move on to a problem-solving scenario. So the diagram below shows the position of a cross-country skier at various times. At each of the indicated times, the skier turns around and reverses the direction of travel. In other words, the skier moves from A to B to C to C to D. Find the skier's speed and velocity. So first of all, let's start with finding the skier's velocity. That's kind of, in my mind, the easier thing to do, because it's very obvious that the skier starts at point A and ends, or in other words, its final position, is at point D. So my displacement divided by my time is going to get me my average velocity. So all I have to do is figure out, well, what was my displacement? Well, the skier traveled 40 meters from point A to C, and then an additional 100 meters to C to D. So my total displacement from beginning to end was a positive 140 meters. Now you might be wondering, why was I explicit in saying positive? Well, remember, displacement has direction. So if I'm treating this like a number line in math class, typically on number lines, the right direction is the positive direction and the left direction is the negative direction. I'm going to use that here as well just to keep my math simple and consistent. So my displacement was a positive 140 meters, and this was done in a total time of 3 minutes. How do I know that? Well, time started at 0 minutes and it ended at 3 minutes, meaning this skier was traveling for a total of 3 minutes. So to find my average velocity, I'm going to take 140 meters and divide it by 3 minutes. Now, when I do this, I end up getting my calculator, an average velocity of 46.7 meters per minute. Now let's focus on speed, because there is a part of the travel, or multiple parts of the travel, that I didn't incorporate in this average velocity calculation. This skier did go all the way from point A to B, a total of 180 meters. Oops, I guess I didn't need to reveal that much. But it went a total of 180 meters, and I'll color code that, because we started here at point A and ended at point B. So this length is 180 meters. And then we went from point B to point C, and that length is a total of 140 meters. And then finally, the skier went from point C to point D, and that length is a total of 100 meters. So by adding all 3 of those lengths up to get my total path length, I end up getting a total distance traveled of 420 meters that I can plug into my equation for average speed, distance divided by time. So the skier went 420 meters, and they did this in 3 minutes total. So when I simplify this, I end up getting an average speed of 140 meters per minute. So looking at my average speed versus my average velocity, I notice that there's a drastic difference in the magnitude of these two quantities. It seems like, according to my average velocity, this cross-country skier is moving a lot slower than they actually were, according to the average speed. So in this instance, it would probably be more beneficial for me to refer to my average speed to describe the motion of the cross-country skier than it would be to refer to my average velocity. That being said, let's move on to another kind of problem. Consider the football coach pacing back and forth across the sidelines. The diagram below shows several of the coach's positions at various times. At each marked position, the coach makes a U-turn and moves in the opposite direction. In other words, the skier moves from A to B to C to D. Find the coach's speed and velocity. So I've marked some points on my timeline that aren't marked on yours. Specifically, I've marked that point C is at the 35th tick mark. Point B is at the 15th tick mark, and point D is at the -5 tick mark. So what I'm going to do first is figure out what's my average velocity. I'm going to do this by figuring out what's my total change in position. My coach starts at point A, which is at a location or a position of 50 yards. And then, as 10 minutes goes by, the coach ends at -5 yards. So this total length is 55 yards, and the direction is in the leftward direction, meaning it's a -55 yard change. So my displacement for the coach is -55 yards. Now, to find my average velocity, I just have to divide my displacement by my total time, and the coach was moving for a total of 10 minutes. So -55 yards divided by 10 minutes gets me an average velocity of -5.5 yards per minute. Now, the coach was pacing back and forth. He was backtracking. So there's a lot of his path length that I didn't consider in my calculation for average velocity. So let's compare this to an average speed calculation. So at first, my coach goes from point A to point B. So this is a length from 50 to 15. That's a total length of 35 yards. I'm trying to figure out a good place to label that, and there might just not be a good place to label that. So maybe I'll leave it unlabeled. Then my coach goes from point B to point C, from location 15 to 35. So that's a total of 20 yards traveled. And then finally, the coach goes from point C to point D. So from 35 yards to -5 yards. So that's a total distance of 40 yards traveled. So let's write that out. 35 plus 20 plus 40 gets us a total distance traveled of 95 yards. So my average speed is going to be that distance of 95 yards divided by the time traveled, 10 minutes. When I simplify this, I get an average speed of 9.5 yards per minute. So I can see that my magnitudes are very different for these two, or for the coach. My average speed is the larger magnitude, but my average velocity has a direction associated with it. So it might be more valuable in this instance to use average velocity, since I can glean from the fact that it's a negative average velocity that my coach must have moved in the negative direction. However, if for the problem that I'm trying to solve, magnitude is more valuable, then I would use my average speed calculation. So to keep this lesson from being too long, I'm going to pause here and start a second part 2 video to complete the rest of the notes. So go ahead and move on to part 2 of this video lesson.